Hi, good afternoon, guys, or whatever time it is for you, I guess. So it's Sunday in Chicago on the last day of January, and we've got about a foot of snow. It's been snowing for about 24 hours. So I'm not able to go to my office and record where I normally would. So I'm in a slightly less fancy setup at home. Hopefully, you can still see me and hear me through this mic just as well. But things aren't quite perfect, and I'm aware of that. And I thank you guys for just being for putting up with that, I guess. So we finished up looking at shear center determination in open sections, and just a reminder, by an open section we meant one for which there are free ends to members like this. So there are two free ends like this, and so we were able to calculate the shear flow in sections like this, and by determining what the shear flow distribution is, we then compared the moments caused by the shear flow and the moments caused by a shear force, and if they were equal, that meant that we were loading at the shear center. So let's just do a quick bit of revision of what we've covered, and then we're going to move on to looking at shear flow distributions in closed sections. So we've gone that far. There's probably some more bits that'll be useful. Let's just do a revision of what we've done. So we've looked at closed sections. No, we haven't. We've looked at open sections. So we had an equation that helps us determine the shear flow distribution within each of these bodies, and that equation, let me just make sure I'm getting the right one down. Qs as a function of s is equal to minus Vy, whatever the y direction force is, divided by Ixx, and then we integrate from s to 0 Ty as a function of s ds minus Vx on Ixx, and then we do the same thing, integrating the thickness and then the x displacement as a function of s ds, where the x and the y in the equation here, so the x and the y here, that's the distance away from the centroid of the section. So like I say, we looked at open sections, and then whenever we started out with one of these problems, we could use some guesswork and some experience to think about the direction of the actual, what this distribution is going to be and what the direction is. So there are some rules that help us with this. So we relied on some things that were going to help us. The first of which is that the net shear force due to the shear flow has to be equal to the net force V that's acting on the section. So this one here, I never actually stated that explicitly during the derivation of all of this work, but it follows from just the fact that it's conservation of energy effectively. We couldn't create some more newtons in the system. So this one here, the way that we actually applied this was by saying that if we've got vertical members and we've got a vertical shear force, then their shear flow direction will be aligned. So it's written here. This means that the parts of sections aligned with the shear force will have a shear flow aligned with that applied force. And in practice, that meant that when we looked at sections like our I-beam, terrible I-beam, but this is the example that we've done here. If we apply a net downwards force, V, then this vertical member will have a shear flow that's going aligned in the same direction as V. We also then said that the shear flow distribution must be continuous, which means that the shear flow must be acting like this. So it's joining up with the heads of these arrows to the tail, and then the same here with the heads of these arrows to the tails of these ones. Got a good image for some other ones, which is one I borrowed from elsewhere. Let me just bring this into the slide. So this simple rule here, like one simple trick, if this was an internet ad, then this is the bit that helps us determine the generalized sort of distribution or the shape of the distribution within different objects. So let me just find this. I borrowed this from someone else on the internet, but this is just a good, I'll share this on the Slack space as well, just an indication of these sorts of shapes with vertical forces, what the shear flow direction must be in those objects. So what else did we use to help us? How were we able to determine the shear flow distribution in these open sections? Well, we were helped by the fact that they were open. And why did that help us? Because if we've got a section like this that has a free end, so this has got 4 free ends, one here, 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 and here, we know that the shear flow distribution at those open ends must be 0. So yeah, let's make that number 2. And that's why when we do these sorts of objects, let's go and say we did our C shape. Again, I'm drawing this with the infinitesimal thickness here. We broke this down into 3 sections, for example, and we said let's call this 1, 2, 3, and 4. So this is then 3 sections. We defined an ordinate going from 1 to 2, which we could call S1, an ordinate going from 2 to 3, which we can call S2, and an ordinate going from 3 to 4, which we could call S3. So QS1, which you could also see, Megson would call this Q12, but I quite like the QS in this sense. Then we define this as starting here. Okay, so imagine if we now apply a shear force of Vy here, then we would be able to say that the shear flow from here to here is given by the equation that we've been using to calculate this. So we'd say QS1 is equal to minus Vy on Ixx, and then we integrate S1 to 0, the thickness, multiplied by the Y, which is a function of S1. Well, even though it's constant for this example, we say it may be a distribution ds1. So we use this expression here. Now, because we're integrating from the location, wherever this ordinate happens to be S1, so i.e., if we're looking for the shear flow distribution at this point, then we're integrating from here to here. So that's why when we have an open end, we can use this expression because this expression here is equal to 0 when S1 is equal to 0. It's actually just this bit, so I don't need to. So it's the fact that this is equal to 0 when we are at the start of these sections, that's what enables us to do this sort of analysis. So when we got to the next part here, I then had to say, okay, well, S2, or QS2 in this case, we'd say QS2 is equal to minus Vy on Ixx integral S2 to 0 thickness multiplied by y as a function of s2 ds2. Now I've left a space here because we don't know what the value is at the start, because it's not open. It would be equal to the end value of what it was at qs1. So we'd say we call this q2, and this would be the principal value q2. So q2 is equal to qs1 when s1 is equal to s1 max. Okay, I haven't written a width on this, so if I'd written b, for example, I could have put b in here, but I haven't. So this here means that it starts with some value, and we then follow this same distribution here. So that's this equation. Let's say this here. This is the generalized expression. We'll say qs is equal to minus Vy on Ixx S1 to 0, thickness Ys ds1 minus Vx. Let's get rid of those ones because I want to do this as a generalized expression. So this expression here is the open section shear flow distribution. If we don't have an open section, then we have an offset that we have to put in the beginning. Okay, we have a constant that we have to add to it. I'll put in here brackets a free end. Okay, so this is only valid for part of the open section with the free end, where we know that it starts at 0. So if we have a section with no free end, then we must know the starting value. Here brackets the offset or the starting value. So that starting value, like we just said here, for this vertical section, the starting value is simply the end value of this distribution here. And then this bottom one, so if we did the C-section, we could look at defining QS3 going from 3 to 4. We'd have to take the starting value of this one here. We could look at this the other way around. You could define your S3 going from 4 to 3, and you'd then find that you'd be able to do just this expression, and then the value at S3 equal to whatever it is that takes it to 3, i.e. the width of the section, you'd get the same value of you get the same ending value that way, okay? So these things helped us do this for closed sections. So we could get the shear flow distribution. So you should now be able to get the shear flow distribution in open sections. So there are those examples in the accompanying notes, some of which I've just borrowed and adapted Megson's examples. You should now be able to go through those, and I expect you to go through them. I'll release some solutions later in the week. Like I've said with that a couple of times, if you just look at the solutions, you can really easily tease yourself into, or trick yourself into thinking you can do it. So give it a go, have a look, see if you can struggle with it, and then look at the solutions and think, oh yeah, that's the bit that I was missing. Now those are quite complicated, those examples, particularly the first one, so I think it's problem 2.2 in the notes. Getting the distributions is actually quite difficult in that question. we don't always need to have the full shear flow distribution to work out the shear center, because remember that's what we're actually looking for in this module. So we want, we'll say we wish to determine the shear flow distribution such that we can determine the shear center of an object. So for our open section, let's draw this where it could possibly be the shear center. Let's say I've got my externally applied force V here, so that must produce shear flows of magnitudes that you guys would be able to determine now. So remember, we said that for an open section, or we didn't say for an open section, we just said in general, but for an open section, any moment evaluated, wherever you want to evaluate it, the moment caused by the applied shear load, mv, is equal to that caused by the shear flow. Okay, so wherever you pick to evaluate those moments, those two are equal if and only if V is applied at the shear center. So that helps us for open sections. Now, this fact helps us quite a bit as well, because then it means that we don't necessarily need to calculate all of the shear flows to work out the shear center. So for example, for this one here, you actually, if you want to work out the shear center of this object, you can, just from symmetry, you can work out the shear flow distribution here. You would then know what the shear flow distribution is here. And in fact, just looking at this, you would only need one of them, because you can choose to evaluate moments here or here, and you've knocked two of those distributions out from producing a moment anyway. So that's what helped us here. Now let's go back to these diagrams up here. What if we've got a closed section like this one here? So we're able to use those rules to help us look and determine what those shear flow, or what the orientation of those shear flows would look like, but we don't know how to calculate the actual shear flow distributions yet, and we've got no idea how to calculate the shear center. No, I said what about open sections? I mean, what about closed sections? To say, looking at that example, let's say I've got a section that's got two dissimilar thicknesses. Otherwise, if I had a section like this and it had the same thickness all the way around, then the shear center would just be at the centroid. So we'll say, I've done this example in the notes. Let's just make sure I'm using the same one from the notes. Yeah, okay, so I've got the one that I've done here. I did, let's call this, let's call these millimeters. 3 millimeters, 1 millimeter. And then the top and the bottom are 2 millimeters. And let's say that we apply a load of 100 kilonewtons here. Okay, so we've got a problem here now. Now we don't know how to determine the shear flow distribution, so we're going to think about how we can do this. So when we were looking at the non-open ends, say in here, to calculate the shear flow distribution in this vertical member, I used whatever the starting value was, sorry, whatever the end value of this horizontal member, that became the starting value for here. So let's go to this one here. So if I was to pretend that I knew the starting value of this horizontal member, I could then produce the distribution, and I'd know the end value here, assuming I knew what this was. That would give me the starting value here, which means I can calculate the end value. Gives me the starting value here, which means I can calculate the end value, which gives me the starting value here, so I can calculate the end value. So there's only one unknown we would have, and that would be whatever this starting value would be here. So we're going to pretend that we know this, or we're going to determine it from another means. And what we're going to do is, for this closed section, we're going to make it an imaginary infinitesimal cut here, and then we'll just treat it like we've got an open section and work out what this offset must be. The way that I've just described that, taking a cut to this, I actually don't really like that vernacular. That's often used quite a bit in other texts you might find for this. So even though I just said that, let's not pretend we're cutting it. Let's just say we know there's some value here. We'll pick a starting position. We know there's some offset value that we need to try and produce. So we introduce a little bit of new nomenclature that's going to help us determine this. So for an open, let's say for a free end. So for a free end, we know that the shear flow distribution is equal to minus Vy on Ixx, and then it's the integral of the thickness multiplied by y as a function of SDS minus Vx divided by Iyy. And then it's the integral from s to 0, thickness, x as a function of s ds. So this then is the shear flow distribution, okay, for an open end. Now, we're going to say that when we've got a closed end, also when we've got a part of a section that exists between two boundaries, if we haven't got a free end, we haven't got a 0, we'll say for any other parts QS is equal to Q0 plus QB. Okay, so we just introduced two completely new bits there, but QB is actually just this. Okay, and Q0 is just this offset. So that's the offset, which is the bit that we're going to determine a number will determine. And then QB is, B is short for basic or open. And it's just equal to this one up here. So even though I'm introducing this nomenclature now, we've sort of been using it, and we used it for determination of the value here. Okay, we already used this, but we just didn't really have a name for it. We didn't have the nomenclature, and you tend not to see this being used, or this expression being written like this, until you start to look at closed sections. So we use this to determine closed sections, and then what we're going to end up with, let's say, well, in fact, we have everything in this problem we need now. So if we were to use this here, the solution procedure would be, let's say, define this as S1, S2, S3, and S4. If we were to start our problem like this, the way that we would solve it is 1. So we would determine shear flow QS1. So QS1 will be equal Q0 minus this whole bit here. Okay, and for this problem, because we've only got a vertical, or we've only got a vertical force, we can actually just copy just the first bit. So let me just do that. Okay, so we could use this. Now, I'll go through a full example of this, but we're going to talk about how we're going to use this first. So we determine the shear flow distribution in this first part of this section, okay, so in S1. Now what we'd end up with here, we'd end up with some function of S1. So I should replace these with ones there, and then this would still be an unknown. Okay, so this would still be a variable, Q0. What we then get, we'd say 2, we determine the principal shear flow at this point here. So we would get Q2 is equal to QS1 when S1 is equal to 200 millimeters for this. And what that would end up being, this would still be Q0 plus some other terms. This would then be, so this would be Q0 plus some other terms. This then gives me the starting value for QS2, and S2 is equal to 0. So we could then determine the distribution in QS2. And if we can calculate QS2, we can calculate QS3 and QS4. So we'd end up with this shape, and we would have all of those. We'd have all of these. We'd have QS1 is equal to Q0 plus some function of S1. QS2 would then be equal to, let's move this a little bit further over. We would have QS2 is equal to Q0 plus a function of QS2. We'd have QS3 would be equal to Q0, which is just the value of the offset that we don't know up here, plus some function of S3, and then we'd have QS4 is equal to Q0 plus some function of S4. And then once we get to this point, we'll double check that we've got the right answer. We'll then do QS4, S4 is equal to S4 max, which I think was 100 millimeters for this, but I'm not going to put the number in. We would check, does that go back to this offset value here, this thing that we still don't know the number for yet? It's just something that we've created. So once we've got all of these, we've got the distributions, and we would have an idea what they would look like. So let me just draw this. Let's say we've got So we might have some so whatever the value that we made up, if we cut it up there, this would then be my Q naught. Okay, so that will be the bit that we don't know, and it's included in all of these other distributions, and we need to determine it somehow. We know how they shape, and we know that effectively, if we don't have that Q naught, that would get subtracted from each of these distributions. So the way that we're going to determine it is from something that's different between open and closed sections. So remember that for an open section, MV is equal to MQ if and only if V is applied at the shear center. For a closed section, MV is equal to MQ wherever you apply that force. So wherever you apply that shear force, that's good. You know that these two are going to be equal, and we can then use this to solve for Q naught. Okay, once we solve for the Q naught, then we're good. We've got our shear flow distribution, which if we've been asked to determine as part of a question, that's great. We've got our shear flow distribution. We know how the shear is propagated through the structure, and you would know, for example, if you were building a section like this out of members that were glued together, that would enable you to determine how much glue or what your spacing and your rivets would need to be between these members, because you know exactly how shear is propagated through the structure. But because when we were looking at open sections, we used this fact to help us determine the shear center, because it was only true when you're loading at the shear center. But for a closed section, that's not the case. We need something else to help us. So we're going to introduce that in the next lecture, or maybe the lecture after that. What I'm going to go through next is an example of actually numerically calculating the shear flow distribution on a closed section, determining what that Q naught is, and how we actually do this when we've got numbers and not just symbols in here. And then we're going to look at determining the shear center. We need to introduce something else. And the way that we're going to introduce this is we're going to look at the equation that determines twist for us. And just so we need a new relationship. Those normally aren't words you want to hear, but we need a new relationship. And so we're going to introduce that. So we're going to produce 2 more lectures this week. The first one's going to be an example of calculating the shear flow distribution in a simple closed section. So that first step is how we calculate that Q naught, and therefore we've got the distribution. And the second one is talking about these fatal words, we need a new relationship, and looking at that. And the way that we're going to determine this is then from looking at the condition that gives us 0 twist. So once I've done that, I'm going to record some examples on calculating the shear flow distribution I'm going to record the solutions to the questions I've given you from maybe not all of them, but from some of those examples. And then I expect you guys to be confident with calculation of shear center. And then we're done with this module, move on to other stuff, and you're going to get a big homework from this. So I'm probably going to have to record from home again tomorrow because the weather doesn't look like it's set to stop snowing. I hope you've all had a wonderful weekend, and I hope you are enjoying the subject, and I I hope you are confident enough to ask me questions on Slack if you want. Put a comment on YouTube. I enjoy the subject. I hope you guys are enjoying it as well. I'm going to produce some more examples, and I hope that you guys have been working really hard to get your way through them on your own. I'll speak to you all next week. Take care. Sorry, not next week, next lecture. Take care.